Natronium, which, as far as I understand, means hi everyone, and let's begin in Russian. Apologies if I got that wrong or if I insulted anyone. Right. A few words about myself before we begin, in case you're wondering. My name is Jonathan Boccara. I run the blog Fluent C++, which is focused on expressive code in C++, and I work at Murex as a team lead of a C++ software team. What we're going to talk about today is the STL algorithms, which are an exciting topic to talk about, isn't it? So I'm going to start off that talk with a question to you. Who in that room is aware of the fact that it's a good thing to know the STL algorithms? Raise your hand. Okay, that's pretty much everyone's hand raising now. Okay. Now, who knows each and every one of them? Come on. Okay, no hand raising, which is exactly the point of that talk. When you walk out of that room in less than an hour, you all know every algorithm that lives in the STL algorithms library as of C++17. The agenda that I will propose is to start with a brief chat about why it's important to know them and what they are, and then we get into the algorithms themselves in a way that I hope will be entertaining. Is that all right? Natronium. So there's this fact that has been popularized over the past couple of years across the C++ community, is that we need to know all the STL algorithms. We need to know them well, very well actually. Why? Well, for one thing, they make our code more expressive by raising levels of abstraction. By raising levels of abstraction, I mean expressing what we want to do in code as opposed to how we want it executed. And I think that's one of the major things to make code more expressive. Other than that, it can be spectacular, the changes that algorithms make in code. You may have seen that talk from a couple of years back from Sean Parent, which was called C++ Seasoning, where it took a chunk of complicated code and managed to refactor it into just a couple of lines, very readable, just by picking the right algorithms. Also, STL algorithms work, right? They're thoroughly tested, they work, and they'd avoid mistakes that we could make if we write our own code managing collections. So if we write code that managed collections, we would write a for loop, probably with somehow sophisticated iteration, and we can get that wrong. I mean, if we do get that wrong and we walk past the end of a collection in C++, then we get into the realm of undefined behavior, and from that point on, anything can happen. Literally, anything can happen. What's happening on the screen right now is perfectly standard C++ when you walk past the end of a collection. Other type of mistake we can make is dealing with the case of an empty loop. Like when you write a loop, you have to do that mental check that it's going to be fine if there's nothing to iterate over, and still there's a risk, and if you do get that wrong, well, that's undefined behavior all over again. Other sorts of mistakes we can make is about performance. There are different ways to write algorithms, and some of them have an astute way to write them to get a better complexity, like algorithms on sets, for example. We'll get back to that a little later on, but some of them can be implemented naively in quadratic complexity, and there are better implementations in linear complexity. And the STL algorithms are optimal, whatever that means, in terms of algorithmic complexity. They're used by billions of people every day. Or maybe not billions of people every day, but quite a lot of people very often. But more seriously, they are part of the common vocabulary of C++. That means that you can use them without fear of not being understood, right? Because they're standard. And what's more, you can use them whatever version of C++ you are using currently in production. Because you can, for most of them, you can go get that implementation. Like imagine you're in C++ 98 even, and you don't have all of or any of copy if, for example, you can just go out on the internet, like cvpreference.com, copy and paste the implementation in your code, and off you go. So most of them, you can use them whatever version of C++ you use. So they're really standard. Now, there's a trap that lies at the beginning of the path to the STL algorithms, and this trap is called for each. For each is one of the STL algorithms. There's nothing wrong with it in itself, but it represents a trap because it looks like a for loop, right? It takes a collection with a beginning and end and a function object, and apply that function to every element of the collection. So it really looks like a for loop. So you may be tempted to think that if you replace every for loop by a for each, then you'd be using the STL algorithms. And that's not quite right, because there's so many of them that can help write code with more nuance. I'm going to show you something to illustrate that there's much more than for each in the STL algorithms library. Ladies and gentlemen, I present you the world of the STL algorithms, the way I see it. So on that map, I've laid out all the STL algorithms as of C++17 and grouped them by family, like how they relate to each other. And that's the best way I know to remember them and be able to go out and use them in code. So the rest of that presentation will be exploring that world. But before we dive in, there are a couple of things we can notice from afar. The first one is that for each, which is up there, is just one of them in an island lost in the middle of the world. Another thing we can note is that most of them lie in that part of the world, which is the lands of queries. Just put that away. Yep. Which means that most of them don't actually modify the collection. I don't know what you think, but I find that quite surprising. I would have expected most of them to do something on the collection, like sort or partition or whatever, but most of them happen to just go out and fetch a piece of information for you in a collection, so read only. Okay, so I suggest that we begin our journey from the other end of the world, from for each, and that would be the algorithms on heaps. So the algorithms on heaps operates on heaps. So what's a heap to begin with? A heap is a data structure that can be represented in the form of a tree, like a binary tree, for example. And there's a property that says that every node is smaller than its children. I think it's called that way because in real life, if you make a heap out of stuff, you want the big things at the bottom and the smallest one at the top. Now, if you look at the heap on the right, it's the other way around, like every parent is bigger than their children, and that's a C++ heap. So in C++, heaps don't look like the real-life heaps, but since we developers don't really live in the real life anyway, does it really matter? I don't think so. Well, to use heaps in C++ with the STL, we need a way to access them as a range, like with iterators for now, with begin and end. So we need to have something that looks like begin and end with that. The way to go about that in C++ is to squash that down into an array or a vector or contiguous structure. Let me do that a little more slowly. So to squash down a heap, or a binary tree for that matter, into an array, we'll just take the first row, which is the root, and then the second row, and then the third row, and so on and so forth. And when we do that, there's this nice property that says that to get from one node that has an index to its left child, it's essentially multiply its index by 2, pretty much. Right, so now that we have that, we can do stuff with the STL on it, right? Because that has a begin and end, can be stored in the vector. The first thing we can make is build a heap. So imagine we've got a range of elements that are not particularly a heap because they don't respect the heap property. Then we can make a heap out of them with std make heap. And that's the first algorithm of the day, std make heap, that takes a collection and rearranges it so that it respects the heap property. Now, to add something to a heap, and that's quite independent from C++, the way to add something to a heap is to put it in the first available position at the bottom, and it's maybe not right, and we make it bubble its way up the tree to its final position by swapping it with its parent whenever it doesn't respect the heap property. To do that with the STL, imagine we've got that into a vector. Then we'd add the thing at the end, and then we use push heap, which is an algorithm on heap, to make it bubble its way up through the tree to its final position. Now, to remove something from the heap, we use something that's called pop heap. Or to remove something from a heap, we can't remove anything. Like, there's only one thing we can remove from the heap, and that's part of the heap thing. We can only remove the root. Actually, the point of a heap, and I didn't mention that, but the point of a heap is to be able to access the largest value in constant time. So that's the root of the heap or the front of the vector, and that's also what we can take out of the heap. So pop heap takes a collection that's supposed to be a heap and start by swapping the largest element with the one at the end, and the one at the end that goes up to the beginning is probably not at the right position because it's one of the smaller ones. So we call pop heap to make it bubble its way down to its final position. Okay? And then actually remove the element with pop back. Now, if we don't call pop back, and if we call pop heap repeatedly on the shrinking heap, then we'll get the larger element, the next larger element, going to the end of the shrinking heap. And if we do that repeatedly, until there's nothing left in the shrinking heap, then we get a sorted collection. Do you see that? Do you see that? Yeah, see you guys nodding. And that's exactly what sort heap does. Sort heap lives at the border between the region of heaps and the shore of sorting, and that brings us to sorting in C++ with the STL. So how do we sort stuff in C++? Well, the simplest way, at least the one that takes the least characters, is std sort. Every algorithm in that presentation is in the std std namespace. I didn't write it every time, but that's std sort. That just sorts a collection, right? Now, there's much more to it than that. One thing, we can sort less than the whole collection. We could sort the beginning of a collection with partial sort. So partial sort takes a collection with a beginning and end, and also an iterator to some position inside of the collection, and it would sort the collection from the beginning up to that position. And what's after that is not particularly sorted in unspecified order. Now, we can be even more precise than that by sorting just one element. What does that mean? That means that we select a position in a collection, so we pass a collection with begin and end and another position inside, and we pass that to nth element. And nth element is going to put the element that would have been there if the whole collection was sorted, and for the rest, they won't be sorted. Not specified to be sorted at all. But the smaller one ends up at the beginning, and the not smaller one at the end. There's sort heap that we've talked about, and there's this last one, which is called in-place merge. That's the incremental step in merge sort, if you know what I mean. So in merge sort, we consider that we have a collection that is made of two parts which are both sorted, and the incremental step sorts them all. Okay, and that's what in-place merge does. And that's it for sorting. Just around the corner, there's partitioning. So, what does partitioning mean? Partitioning is about looking at a collection through a predicate. So, say in this example that the predicate is being blue, okay? And partitioning a collection with regard to being blue is putting the blue ones at the beginning and the other one at the end, okay? And the position that's sort of in the middle, that's the end of the blue ones and the begin of the white ones, is called the partition point. And you can get that with stood partition points from the STL. Well, let's take a step back. We've been around the lands of permutations that change the order of the elements of a collection without changing their values. There are a few others in the lands of permutation over there, and we're going to go through those quickly. So the other permutations. How can we rearrange a collection? Well, there's this one that has been made famous a couple of years ago, I suppose. That's rotate, that makes cyclic permutations. So the elements at the back go up to the front. Okay. Now, another way to change the order of the elements of a collection is to change it randomly, right? And that's what chock-full does. So you pass it a random number generator, and it would rearrange the collection randomly. Now, there's an order in permutations, right? So all the given ways to rearrange a collection, they can be ordered in a lexicographical way, right? So imagine how words are ordered in a dictionary, okay? And we can order words in a dictionary because we can compare letters. Now, if we can compare elements in a collection, we can order the permutation the same way that we order words in a dictionary. Does that make sense? Cool. And to move from one permutation to the one that's just after it, in that order, that would be next permutation, and the one before it, prev permutation. That can be useful if you want to do something for every possible combinations of some elements, and you do next permutation that takes the beginning and end repeatedly until rolling over back to the beginning. And the last one, which is probably the simplest one, is reverse, that reverses a collection. All right? Now, before moving on, there's this wreck off the coast of chock-full. It's wreck as in it's deprecated. It's the way that used to be the good way to do a random chock-full, but it's deprecated in favor of chock-full, so we don't use it anymore. You use chock-full. Okay, in that corner of the map, that's the secret runes. The secret runes, that's how I like to call them, are things that can be combined with an algorithm to make it get new paths. I call that runes because it's like you can go to rune and be augmented in your paths, doing new things, but that looks like what you were doing before. Also call that runes because I find that cool. So the runes we can know now are stable, which combine with algorithms to keep relative order of elements, like stable partition, for example. Because if you remember partition, all the blue ones ended up at the beginning, but they may have changed order. If you don't want that to happen, use stable partition. Same thing for stable sort. Now, we know what sorted means, partition means, heap means. Well, we can check for a collection if it has this property of being sorted. So those guys return a Boolean. And there's a variation that return an iterator to locate the first position where a collection is not respecting that property anymore. So is heap until returns an iterator that represents the point after which the collection is no longer a heap. Okay, let's take a step back. So we've been around all that corner, um, all that corner of the map. Now let's move on to the largest chunk, which is the lands of queries, where most of the algorithms are. In the lands of queries, there are several kind of things you can get from a collection. That would be like searching for a position or getting a value, that kind of thing. Most of them live there, but it wouldn't be that long to go all over that region. So the simplest one is count. Count takes a collection, beginning and end, and a value, and returns how many times that value occurs in the collection. So in that collection, if you count for x, that would be 3, right? Accumulate makes the sum of the elements of a collection. You can replace the sum with whatever operations you'd like. And in C++17, there is reduce that came in the language that does pretty much the same thing as accumulate, except that it can have an overload without initial value, and it can also be parallelized. And there's transform reduced, also coming in C++17, that takes a function, applies it on the value of the collection, and then performs a reduce, right? So that transform reduce. Partial sum makes the partial sum on a collection. So the output of partial sum is a collection where the first one is like the input, the second one is the first plus the second, the third is 1 plus 2 plus 3, so on and so on. And there are inclusive and exclusive and transform scan, which look a bit mysterious, but they do pretty much the same thing as a partial sum. So inclusive scan is kind of like the same thing as partial sum, except it can be parallelized. An exclusive scan is like inclusive scan, but it doesn't count the current element. So in exclusive scan, the second element would be equal to the first, and the third would be 1 plus 2, and the fourth would be 1 plus 2 plus 3. Do you know what I mean? Right. Inner product makes the inner product, and perhaps more. But essentially, the inner product is combining two collections, multiply them 2 by 2, and add the whole thing together. Adjacent difference makes the difference between two consecutive elements. So the second one becomes 2 minus 1, the third one becomes 3 minus 2, and so on. And sample takes a random number generator and would go and pick out some elements for you. Like you give it a number of elements you want, and it would go and fetch those elements and pick them at random in the collection. That was for querying values. Now we can query a property. So there are 3 generic algorithms in the STL to query a property. That would be all of, any of, and none of, that has to do with predicates. So all of takes a collection and a predicate and returns the Boolean saying if all the elements of the collection satisfy the predicate. Any of, if at least one element satisfies the predicate, and none of, if none of the elements satisfy the predicate. Now we can wonder what happens if you pass an empty collection to all of. What do you guys think? There are only 2 possible answers, so even if you answer at random, you have a 50% chance of getting that right. What do you reckon? Yeah, that's true. You can think of it as coming from maths, where for anything in the empty set, whatever property follows is always true. Or you can see it as a convention, but whichever way, it's good to know. Now, any of, for an empty collection, what do you think? True, false. One of you is right. Yeah, that's false, because it's not true that at least one element satisfies the predicate. And how about none of? Yeah, true. That's the opposite of any of. Okay, now querying a property on 2 ranges at the same time, that consists in comparing ranges, essentially. So the easiest way to compare ranges is stud equal. So stud equal returns a Boolean that says if it's exactly the same contents. So exactly the same values and the same order and same size, right? Now, if you'd like to know if it's the same contents but not in the same order, maybe, that would be is permutation, also returning a Boolean. Now, to compare 2 collections to see which one is smaller, well, we could compare the size, but there's a more precise way to go about it, and that's, once again, comparing them like in a dictionary. So this is a collection of letters, but that could work with any element that can be compared. And you can see that the left one is smaller in the dictionary order than the right one, right? So that's lexicographical compare and also returning a Boolean. Now, the last one of the three is mismatch. So mismatch traverses the two collections and stops whenever they start to differ, right? And it would return the position where they differ in the form of a pair of iterators pointing to the first position where they start to differ in each collection. Right, so now let's get into searching. There are essentially two ways to search, right? That would be if the collection is sorted, you do binary search, and if it's not sorted, you have to go all the way through the collection to find what you're looking for. So let's start with the not sorted, because that's the simplest one. Well, there's find. Come on then. There's find, obviously, stood find. Returns an iterator, or end, if it doesn't find it. That's a famous one, but it has a sibling that's not as famous, but quite useful, which is adjacent find. That returns the position where you have two consecutive values that you're looking for. Quite useful. Now, on the sorted side, well, if you're looking for something like you're looking for the orange in that collection, then there may be several orange in that collection, but they will all be together because the collection is sorted, right? So what you're looking for is more a range than a value, like a sub-range where the orange values are located, and that's what equal range returns. Returns it in the form of a pair of iterators, which is quite unfortunate because it doesn't return a begin and an end, even though it's arranged, but that's how it is. Now, there are lower bound and upper bound, which are not really for searching a value, but rather to search a position, like where would the orange value be located if it was there? And lower bound would give the orange, well, the value at the left of the existing orange value, and upper bound at the right of the existing orange values. But if there's no orange value here, lower bound would not return the end like find does. So it's not really easy to use just for search something that would be equal range. And there's this last one, binary search, which is a bit surprising because, well, it performs a binary search, which is a good thing given its name, but it returns a Boolean that says whether or not the element is there and not the position where it found it. Now, that was searching for a value. We can also search for a range inside of a range. So we've got, let's say, a small range, and we'd like to locate it in a big range, and that's search. And that's very unfortunate, isn't it? Because it looks like find, but it really doesn't do the same thing as find. And search returns the first occurrence of the subrange, and if you'd like to have the last occurrence of the subrange, that's an algorithm with an even more unfortunate name because it's called find end. That's weird, isn't it? That's how it is. Now, if you'd like to find the first occurrence of any value of the small range inside of a big range, that's find first of. Right? Now, finishing off with search, searching for a relative value, that would be like the largest one or the smallest one. So the largest one you get with max element returning an iterator pointing to that location where the max element is, min elements for the min one, and if you'd like to go both, to get both at the same time in one single pass, that min max element returning, quite expectedly, a pair of iterators. All right? Okay, moving on, we've been all around the land of queries, moving on to my favorite part of the world, that's the algorithm on sets. They live in a glorious country, because they're glorious, I think. So what's a set to begin with? In C++, a set is a sorted collection. So that can be a stood set, but that can also be a sorted vector, for example. So the algorithms on sets take sets, a sorted collection, and produce other sets, other sorted collection, and they do mathematical operations on set, like set difference, for example. Set difference takes two sets and returns, via an output iterator, the elements that are in the first one, but not in the second one. And that's so useful. That really comes up often, doesn't it, as a use case? And that would be really difficult to implement, and this is linear in complexity, so that takes some time to implement, I think. But you can do that in one line with set difference. Set difference has siblings. Set intersection that gets the values are both in A and B and returns the version from A. Set union that returns everything. Set symmetric difference that returns the element that are in B, but in A but not in B, and in B but not in A. Includes that returns a boolean to indicate whether all the elements of B are in A, and merge that takes two sorted collections and returns a sorted collection that contains everything that was in both collections. And that's it for set. Went really fast. Let's take a step back. So we've been in the lands of permutations, in the lands of queries, and up there in, come on then, in the county of sets. So we've been in the majority of the regions. We have all those to finish, and then we'll be done. So moving on to the movers. So the movers, they transfer data from one place to another place. The simplest way to transfer data is probably to copy it. So that stood copy, which is maybe the simplest algorithm of the whole library, takes a beginning and end and an output iterator and copies every element between the beginning and end to the output iterator. Now, if you'd like to move every element and not copy it, that's stood move. You may know stood move, like the stood move that we use every day on one value, but this stood move is a bit less famous. I didn't know it until recently. And it calls a stood move on every element of the collection and moves it to the output iterator. If you'd like to exchange the values of two ranges, that would be swap ranges. Right, now let's make a little exercise. Imagine that we have the collection at the top, 1, 2, 3, all the way to 10. And we'd like to make it reach the state at the bottom, right? So to copy the elements from 1 to 5, 4 positions down. What algorithm would you use to do that? There are about 105 possibilities, so if you answer randomly, you may get a wrong answer. Yeah, so we've got copy with reverse iterators. Or, yeah, it's kind of something like that, I think, although in this particular case, reverse iterators would, I think, output 5, 4, 3, 2, 1 instead of 1, 2, 3, 4, 5, I think. But you're right that it looks like we should use copy, but copy is not the right algorithm. So you probably saw why. Because if we use copy, then we'd start by copying the first element, and then, oops, we lost 4, right? So we need to, like you're saying, start at the end, like copy the last element, and then the one before that, and then the one before that, and all the way up. Yeah. So we'd need to do a copy, but backwards. So we can use copy backwards. And there's also move backwards that does the same thing, but moving. Okay, just around the corner is the land of value modifiers that actually go and modify values, and you can see how scarce that land is. I find that surprising. Do you know what you think? So the algorithm that changed the values of a collection, the first one is fill. So fill takes a collection, begin, end, and value, and puts that value everywhere in that collection. Generate does something fairly similar, but it doesn't take a value. It takes a function that you can call with no arguments, and it calls that function with no arguments as many times as there are elements in the collection, and fills the collection with the return values. There's iota, which has a funny name, that takes a value, puts it at the first position, and then increments it, and fills out the whole collection with those incremented value. And then replace, which is the simplest one, that replaces values. So in that case, we'll replace every 42 by 43 in the collection. Right, moving on to the island of structured changes. By structured changes, I mean that after those algorithms, the collection doesn't look the same from afar. So that's about removing things from a collection. To remove things from a collection, like say removing a value, we use remove. Yeah, but algorithms don't have access to a collection. They can only access the value through iterators. So they can't actually remove something, like they can't change the size of a container, for example. So if you have a vector and like to remove the 99s from it, it could remove, that would do its best to remove the 99 then by squashing up the collection and removing the 99. But you still have things at the end. So you need to call the erase method of the vector from the first position where there's nothing interesting to the end, right? And remove returns that first position. So you need to call erase of what remove returns and do that to the end. And that's a lot of code, right? Just to say remove the 99th, right? That's really a mouthful. So what we should do, I think, is to wrap that just once in a function that has a nice interface. I think there has been a proposal for the standard to have that, but it's not the case yet. So until then, let's do that in our code base. To remove duplicates, we use unique. That will remove adjacent duplicates the same way remove works. So it returns an iterator, have to call the erase method on the container, and should probably wrap it in a nice interface. We've unlocked a rune, the copy. So copy can be combined with algorithms to be read-only on the collection, on the input collection, and output the results through an output iterator. Right? So remove copy doesn't actually remove anything from the collection you're passing, but it would output all the values that are not 99 in an output iterator. We've also unlocked if, that takes a predicate instead of a value. And we're moving on to this lonely part of the world where for each lies, and also transform, which I couldn't quite fit into a family, although they're quite useful. So transform is about applying a function to a collection, to every element of a collection, and takes an output iterator that can be the begin of the collection you're passing as an input, or something different. What's a bit less famous about transform is its second overload. So it has another overload that takes two collections and a function that takes two values, and it applies that function on both collections and output that values to an output iterator. And that's quite useful if you like to, say, sum the elements of two collections 2 by 2. Transform lets you do that in one line of code. And for each, the famous one. So for each applies a function to every element of the collection and doesn't care about what that function returns. So that function, as far as for each is concerned, might as well return void. And that gives us a hint on what for each does. What do you think a function that returns void does? Side effects, because it doesn't return anything. So for each is made for side effects. It's not made to replace a for loop in general, it's made for side effects. Now, I'm not saying that it's a good thing or a bad thing to make side effects. I think they can be useful in some places, but for each is made for side effects. Now, let's take a step back. We've been all around the world, literally, all around those places, except for that last part. Raw memory. So what is raw memory about? Yeah. So remember fill and copy and move. They all share something. They have something in common, and that would be that they use the assignment operator. If you use the assignment operator on an object, then you're assuming that its constructor has been called already. And hopefully that's true. But imagine that you have a chunk of raw memory that somebody passed on to you, like shared memory or whatever, like a chunk of raw memory. Well, you can't fill it with fill because it's just raw memory. It hasn't been initialized. This is why there's an initialized fill, an initialized copy, and an initialized move that call the constructor instead of the assignment operator. So they would call the constructor that takes a 42, or the copy constructor, or the move constructor, but they would initialize that chunk of memory with stuff through its constructor. And when you're finished with using that chunk of memory, you have to call the destructor on every element of that collection, and that's what destroy does. So destroy takes pointers, like the initialized algorithms do, and would call the destructor of every element in that collection, so that you're back with a chunk of raw memory, and you can hand it back to whomever passed it to you. Now, if you'd like to initialize that chunk of memory with default construct or value construct, sorry. Oh. There we go. With value construct, an initialized default construct and an initialized value construct would do that for you, and happily. We've unlocked the final rune, _n. That's a variation of the interface of the algorithm. So most algorithms take a begin and an end, right, to locate the input collection. Well, the _n algorithms do the same thing, except that they take a begin and a size. So remember fill, for example. Fill takes a begin and an end in 42, and fill n takes a begin and a size. So that would fill the first 5 elements of a collection with 42s. Does that make sense? Cool. Now, what do you think that makes? Let's say that collection is an empty vector. What do you think happens after that line of code? Anyone an idea? There's an infinite number of possibilities. Or that fill n would pass 42 5 times to the back inserter and increment it every time. But when you increment the back inserter, you're not doing anything. So it would just pass 42 5 times to the back inserter. That would push back 42 5 times in the vector, so you would end up with a vector of 5 42s. All right? Okay. We've been all around the world. You know everything. You know every algorithm that lives in the STL algorithms library as of C++17. Now what? What are you going to do with that? Well, for one thing, you can use them in code to make your code more expressive. You can fine-tune your intention and go and use the right algorithm that fits what you're trying to express instead of a for loop. If you want, I'm happy to have a look at code and suggest algorithms to use. If you have a feel for, like, there's an algorithm that could be used here, just reach out to me. Now, if you'd like to see more algorithms outside of the STL, there are a bunch of them in Boost. Most of them are in Boost algorithm, but some of them are scattered across various libraries in Boost. To go further, I suggest that you do spend time studying the algorithms. I think it's worth it. What you can do is learn their algorithmic complexity, or their prerequisite, post-requisite, like which of them expect a sorted collection, for example. And look inside. Look at their implementation. Try to implement them yourself. That will give you an intuition about how they work and what are their post-requisite, prerequisite and stuff. And get inspired. when you're familiar enough with the STL, it sort of comes off on your coding style because you've got a feeling for what good abstractions look like. And when you're familiar enough, you can start writing your own algorithms because you know how those things work. So what sort of algorithms could you write? Well, you could combine an existing algorithm with a rune and create a new combination, like sort copy, for example, doesn't exist. Or you could add a city on the map, enrich the family. If I had to add one, I think I'd add something in the algorithms on sets. I think I'd add an algorithm that would take 2 sets and return in one single pass 3 output iterators with the elements in A not in B, the elements in both, and the elements in B not in A, I think. Or you can start a family. If you'd like to get the map, just go on fluentcpp.com/getthemap, where you can download it, or you can buy a poster. And actually, for the people in the room, if you're interested in getting the poster, I've got a bunch of them here, so you just come and see me after the talk. Other than that, if you'd like to chat about things, connect, follow me, whatever, follow me on Twitter. And if you'd like to get hold of me, I'm happy to talk to you on Fluent C++ on the blog. Thank you. Have we got any questions? Yeah, here, question. Okay, there.
Many thanks. Have these algorithms been optimized for graphical processor units, or is it for CPUs usage only?
So if I understand the question, you're asking how algorithms are optimized for CPUs and GPUs, is that right?
Yes.
I think, yeah, it's a long answer. It takes an hour or something, and it should be answered this afternoon, no, tomorrow afternoon by Simon Brunn, just over here. So I suggest you go attend that talk. Any other question? Yeah, there's a question here.
Thanks for your talk. Just a short question. Do you have a more elaborate guide about what you just said, maybe written, or a book, an article or something, with the complexities and implementations, inlines, something like that?
Yeah, right. So about, well, if you want all details, all possible details about complexity and stuff, you can go on references, but I guess they're a bit hard to read if you want to read everything. There are a few talks that show some of the implementation of algorithms, like stable partition, I think. Sean Parent has made those talks. Like, if you look at the keynote of Meeting C++ to 2017, last year, you see Sean Parent talking about that. Now, I think that on the website of Alex Stepanov, there are quite a few papers delving in the STL implementation. And if you'd like to see like practical things about things to do, things to avoid, use cases and stuff, just go on fluentcpp.com/STL, where I write quite a lot about that. Other questions? Yep, Raina.
Thanks a lot. Do you know why iota is called iota? I know it's a Greek letter. I know it's an old mathematical expression, but I don't know why.
Yeah, it's a good question. Well, I think it comes from another language, which is called ACL, is that it? ABL, yeah, right. But that doesn't answer your question, right? That answers your question from a C++ point of view, but I have no idea why it's called that in the ABL language. Other questions? Yep.
Yeah, regarding binary search, I find that one common pitfall for people learning to use it the first times, you mentioned binary search that returns a boolean. That's pretty much useless. But in terms of using lower bound, for example, many people don't properly use the correct idiom in checking the result of lower bound and in making sure the referenced returned iterator actually holds the value that you've searched for. Because if the value is not existing in the range, lower bound would return the position where it should be in the sorted range. So I think I just think this kind of gotcha is something that holds back developers in using binary search, for example, from STL. What's your opinion on better improving on those, on teaching those idioms for beginner developers?
Do you mean lower bound and upper bound?
Sorry?
About lower bound and upper bound, right?
Yep.
Yeah. Well, I guess that's one of those things that you have to know. You have to learn because, yeah, as a beginner, you can't really guess that.
It's definitely not intuitive. So.
Absolutely, yeah. I know that, well, Scott Meyers writes about that in Effective STL. So you can read that book. I've talked about it a little on Fluent C++ too, but I think it's not one of those things that you can wrap into a nice interface like unique or remove. Those things, I guess you have to go through learning them, and I agree that it's not convenient. Yeah, you're right.
Hello, thank you very much for the lecture. It was really very fast.
Cool.
So I'd like to ask a question about the difference between transform and for each.
Yep.
You give a bit description of that, but I'm a bit out of theme. Could you please repeat?
Sure, no problem. So transform, let me put that slide back up for transform. So that's transform. So if you notice in transform, there's an output iterator. Oh, it's not working. Oh, whatever. There's an output iterator. So for one thing, transform can output things in a different place. Whereas for each, it's just locally, right? You apply a function on a collection in place. Okay, that's one difference. Another difference is that with transform, you have the semantics of assignment, because the output of the function, when it's applied, gets assigned to the output, right? So if you have an existing output, you get the semantics of an assignment, which is not the case of for each. We just apply the function. Okay, so I think that for each is more explicit that it's going to make side effects, right? In transform, you could, in theory, make side effects, but that would be confusing, I think, because this is the semantic of just applying a function, getting a result out of it. Those are the practical differences. Now, there are legal differences as well. Like, for each is required to traverse the collection in order, right? Whereas transform has more freedom to treat it in any order, even though it has to output in the same order as the input. Does that answer your question?
Yeah, thank you. Am I right that, for example, the transform, it's very close for something like a map for functional programming?
You're absolutely right. Transform is pretty much equivalent of map in functional programming.
Okay, thank you very much.
And no problem. And actually, the other overload that takes two inputs is the equivalent of zip with in functional programming. Are there questions? Yeah, there's a question there.
Am I understand right that raw loops still have sense if we want to process more than one or two ranges, because, for example, we want to iterate over three iterator range and do some operation over that, so we don't have any STL for function to make it.
Right, yeah, that's a very good point. Did everyone hear the question? Should I repeat it? Anyone wants me to repeat the question? Yeah, okay. So the question was, do you think that raw for loops still make sense in the case where you're treating several collections at the same time, like 3 collections, for example? Because we've got plenty of them for 1 collection, we've got transform for 2 collections, it just does transform, but there's nothing for 3 collections. And there are things that transform can't do for 2 collections, so you're absolutely right. Well, if you're just using the STL, then yes, in that case, I would say that it makes sense to use a for loop if you want to use several collections at the same time. Now, that said, I think that's a use case for writing your own algorithms, because in general, independently of the STL, manipulating several collections at the same time is something that can be extracted and that can be reused several times over. So you can make some sort of for each or some sort of transform, some sort of whatever that looks like the STL algorithms but takes more collections, and I think that makes a lot of sense. Now, going back to Arno's talk just before me, he was talking about ranges and ranges adapters, and I think that's one thing that ranges adapters can do also. Right? Do we have other questions?
We run out of time.
Okay.
So any other questions could be asked privately. Thank you again for this great.
Yeah, no problem. If you have a question, I'll be out in the hall, and if you're interested in the map, in the poster, just comment to me after the talk. Thank you.